Okay, so today we shall talk about some comments on the security of RSA. So we have been discussing about the RSA algorithm, and today we shall essentially talk about certain topics like we shall basically analyze the security of the RSA algorithm. Okay, so the RSA is a wonderful algorithm, but we shall see that there are certain properties which the RSA ciphertext leaks about the plain text. Okay, so we shall try to identify those things and analyze them. Okay. See, for example, the first thing that we shall discuss is that computing the phi n or the Euler-Thorsen coefficient is no easier than factoring n. So, we shall discuss about this point, and then we shall discuss about the point that if the decryption or exponent is leaked, okay, then actually somebody can factor the value of n. Okay. So, therefore, this is actually of lot of practical relevance, okay, because the fact that if the decryption exponent is leaked, then not only you need to change the decryption exponent, but you also need to change the value of n. Okay. So, and then we shall discuss about another topic, that is the bit security of RSA. That means, we know that RSA as a whole is quite secured. If we assume that is, for example, I mean, does it leak any information about the bits of RSA plain text, like maybe the 0th bit. Okay. So, the entire thing may be hard to find out, but if I am interested in a partial information. Okay. So, this is actually, we start with a very simple thing. So, we know already this, but as a revise, we know that computing phi n, if we know the value of phi n, that is if the value of n and the value of phi n are already known to us. Okay. So, then the question is that if n is a product of two prime numbers, say p and q, okay, then n can be factored by n. We know that n is equal to the multiplication of p and q, right. And what is phi n? Phi n is a product of p minus 1 and q minus 1. So, suppose we know the value of n and we know the value of phi n, then if we can actually combine these two equations, and we can write, if I combine this equation, that is n equal to p q, and if I combine phi n equal to p minus 1 q minus 1, then I can write this quadratic equation, okay, because we know that we can express this as p q minus, if I take common p plus q plus 1. So, therefore, if I plug in the value of p q equal to n, then we obtain this quadratic equation, and the roots of this quadratic equation will be the values of p and q. So, which means that if I know the value of phi n, then I am able to find out the value of p and q, I am able to factor n. Okay. So, therefore, we know that actually the computation of phi n is no easier than factoring the value of n. Okay. So, this is a simple implication that we can understand. The other important thing that we shall discuss is that about the decryption exponent. So, as I told you that if the decryption exponent is known, okay, then n can actually be factored. Okay. So, we shall actually study a randomized algorithm. It is quite simple to understand the randomized algorithm. There has been recently in Crypto 2004 a paper by a person called Alexander May, where a deterministic algorithm for this was also proposed. Okay. So, we really now have a deterministic algorithm for this, where there are certain conditions which are quite practical and practically true, like a and b are roughly of the same bit size. So, what is a and b? A is the encryption exponent and b is the decryption exponent. Okay. So, a and b are roughly of the same size, and a b is in general lesser than n square, and the runtime of this algorithm is O log square n. So, therefore, it is a polynomial time algorithm. Okay. But what we shall study is essentially an example of a randomized algorithm. Okay. It will be of a La Vega class. Okay. So, we will study that. So, what is the importance of this result? It is also important from the practical point of view, because the idea what we are trying to say is that if the value of b or the RSA secret key is leaked, okay, then one can factor the value of n with a reasonably high probability. Okay. So, that means that if the value of the b is leaked, then if I still want to use RSA as a for further communication, then it will not suffice to change the value of b only. You have to change the value of the modulus also, because the modulus is factored, and you know that the security of RSA is, there is no security if you know the product, if you know that values of p and q, if you know the factors. Okay. Is it clear, right? So, therefore, we shall actually study a La Vega algorithm which can actually factor in with a probability of at least half. Okay. So, we shall not really argue why is the probability, but we shall see that we have a randomized algorithm which will do that. Okay. And if you are interested in the proof for at least half, you can follow Stinson, the proof is detailed there actually. Okay. I will not go into the proof, but we will just try to analyze the algorithm and try to understand why it works or why it should work. Okay. So, in order to understand that, again we have to rely heavily on number theory. Okay. So, therefore, we shall actually take a very simple question, that is, suppose we have this equation where x square is congruent to 1 modulo n. Okay. So, therefore, how many roots does this equation has? You know that n can be factored into two values p and q, right. So, n is a product of two prime numbers p and q. Okay. So, this actually has got how many roots, that is the question. So, therefore, there are, I mean, if you follow or if you study, then you will find that there are 4 roots. Okay. So, trivial 2 roots are quite easy to understand, it will be plus minus 1 modulo n. Okay. But there are 2 more roots which are actually non-trivial roots. Okay. Can you guess why, or how can you reason why there are 2 roots, 2 more roots? X square minus not really. So, yes, if the clue is that you have to take the value, take the clue that n can be actually factored into two values p and q. Okay. So, therefore, now you remember something which is called a Chinese remainder theorem, right. So, therefore, if I apply Chinese remainder theorem, I can get 2 more roots. So, therefore, I mean this equation, that is x square equal to 1 mod n or congruent to 1 mod n, is equivalent to the system of equations or simultaneous equations, which is x is congruent to 1 mod p and x is congruent to 1 mod q, or rather x squared is congruent to 1 mod p and x squared is congruent to 1 mod q. Okay. So, therefore, what I am saying is this, that is the equation x square is equal to 1 modulo n, okay, is actually, I mean, equivalent to this system which says that x square is congruent to 1 modulo p and x square is congruent to 1 modulo q. So, then in Chinese remainder theorem we had this property that p and q had to be relatively prime, right. So, in this case p and q are prime numbers. Okay. So, this equation, that is x square is congruent to 1 modulo p, has got 2 roots. We have studied this already, right. What are the 2 roots? The 2 roots are actually x is congruent to 1 and x is congruent to minus 1, but modulo p and also modulo p here, right. How many roots are there here? There are also 2 more roots. One is x is congruent to plus 1 modulo q and x is congruent to minus 1 mod q. Okay. So, now these 2 things, that is plus 1 and plus 1, will give me a one trivial root, and again this combination will give me another trivial root, that is plus 1 and minus 1. But there can be other combinations, right. So, you can take the plus 1 from here and the minus 1 from here. So, this, that is x is congruent to plus 1 mod p and x is congruent to minus 1 mod p or mod q, will give me another, actually should give me another root, right. So, this actually gives you one non-trivial root, and similarly the other non-trivial root is just the opposite, that is you take x is congruent to minus 1 mod p and x is congruent to plus 1 mod q. Okay. So, therefore, these actually should give you 2 more non-trivial roots. Okay. So, can you tell me why are we studying non-trivial roots? Because our objective is to factor n, right. So, what will, I mean, from the previous day's discussion, can you give me an answer to this? Why are we at all interested in finding out a non-trivial root? Okay, I will give you a hint, that is x square is congruent to 1 mod p or rather 1 mod n, and I tell you that x is actually not congruent to plus minus 1 mod n. So, these are the trivial roots, right. So, in that case, what can you say about the factors of n? How can you compute them? So, x is not congruent to 1 plus minus 1 mod. Okay. So, from here you know that n divides what? X square minus 1, right. So, therefore, this says that n divides x minus 1 into x plus 1, but you know that n does not divide x plus 1 or x minus 1. So, what can you say? So, n is what? The product of 2 primes p and q. So, what does it say? So, p divides suppose x minus 1 and q will divide x plus 1, right. So, one way of factoring n would be to take the greatest common divisor of say x minus 1 and n, right, because you know already one factor, right. So, if you take the, so you know that p divides x minus 1, okay, and if you get a factor from here, then you know that that non-trivial factor, if you take as say x minus 1, if you take x minus 1 and if you take n and if you compute the GCD, you should get one possible factor of n, because you know that p divides x minus 1 and p also divides n, right. So, therefore, this can be one way of factoring the value of n, right. So, we are interested in therefore finding out non-trivial square roots of 1. Okay. This philosophy is same as that we have seen in the previous algorithms. Okay. So, we have got more examples to clarify this point. So, let us consider this like 403, which is a product of 13 and 31. Okay. This example 13 and 31. So, you have got suppose what I am interested in is to compute the solution to the system y square is equal to 1 modulo 403. Okay. And this system is actually equivalent to y square is equal to 1 mod 13 and y square equal to minus 1 mod 31. Okay. So, this has got two roots plus 1 minus 1 plus 1 minus 1 mod 13 here and mod 31 here. Okay. So, this is a typo mod 31. Okay. So, now if you take these two systems, that is x equal to plus 1 mod 13 and x equal to minus 1 mod 31, you see that you get one root which is x equal to 92. Okay. So, you see that 92 satisfies both these equations, because if you take 92 and divide by 13, you get a remainder of 1. If you take 92 add plus 1, you get 93, which is divisible by 31. Similarly, in this case also. Okay. So, therefore, this system gives you two non-trivial roots, two further non-trivial roots. Okay. And now, the idea is this, that is, if x is a non-trivial square root of 1 modulo n, then x square is equal to 1 squared mod n, but x is not equal to 1 mod n. Okay. So, then what we do is that we compute the GCD of x plus 1 and n and GCD of x minus 1 and n to get the factors of n. So, in this example, you see that if I take 93 and if I take 403 and I compute the greatest common divisor, I get one factor 31. Similarly, for this case, if I take 91 and if I take 403, take the greatest common divisor, you get 13. Okay. Right. So, therefore, this can be an easy way of factoring, but the thing is that we need such values, that is the catch, right. So, therefore, we have to get some values like that. So, you see that, so therefore, the objective now is that we need to calculate these values which are actually non-trivial square roots of 1. Okay. And that means non-trivial means the square roots are not plus 1 or minus 1. So, what we shall see now is that how we can actually exploit the idea or the knowledge of the decryption exponent to find such values, right. So, you have to see that. So, let us go through this algorithm step by step. So, what it says is that, so you know that what we have to do, we have to factor the value of n. Okay. And suppose you know that there is an algorithm say A which actually gives you the decryption exponent, like if you, it is like an oracle, like if you ask that question that okay, this is the public exponent, give me the private exponent, it can give you that. So, assume that there is an oracle. Okay. So, therefore, now what you do first is that you choose a w value at random. So, just choose one random value which lies inside 1 and n minus 1. Okay. So, from this field you just choose one arbitrary value and you compute the GCD of w comma n. So, if you find that this is actually something which lies between 1 and n, that means it is a non-trivial factor, then I must say that you are very lucky, right, because that means you have found out the factor straight away actually. But this will not in general be the case, right. So, therefore, what we will do is that we will go ahead and what we will do is that we will use this oracle, which if it is queried on this B gives me back an A, that means it gives the decryption exponent. Okay. So, if you ask give the public exponent, it gives you suppose the decryption exponent. Okay. So, then what you do is that you suppose you factor, I mean you know that AB minus 1. So, what is AB in this case? You know that no, AB is not n, AB is the encryption exponent and the decryption exponent. If you, I mean they should be ideally equal to 1 mod of phi n, right. So, that means that AB minus 1, okay, yeah, will be equal to 0 mod phi n, that is true. But the thing is that AB minus 1, okay, so P minus 1 is what? P minus 1 is actually an even number, right. So, in that case AB minus 1 also should be an even number, you see that. So, that means there should be definite some factors of 2. Okay. So, what we do is that we first of all take out all the factors of 2 and we are left with an odd factor. right. So, a b minus 1 I can factor in this way, which is say 2 to the power of s into r, where r is odd, right. So, we can do this factoring quite easily. Okay. Taking out factors of 2 is quite easy. How? What will you, how will you implement? Just see the trailing zeros. If you just write them, you just see the trailing zeros. Okay. So, then what you do is that you compute the value of w to the power of r. So, you have chosen one value of w, and this is the r, which is the odd value, and you choose a w to the power of r value mod of n. Okay. So, you get a value of v. Okay. So, if v is equal to 1, then actually it is a failure. Okay. So, then what I am saying is that it is a failure. Okay. Otherwise, what we do is that means if v is not equal to 1, then what we do is that we try to find out the squares of w to the power of r. Okay. So, we calculate w to the power of r, w to the power of 2r, and so we calculate the squares. Okay. So, wherever you get a 1, you actually quit this loop. Okay. And what you see is that whether the value of v naught, that which is the previous value. So, you see what we do in this loop, we calculate the square, but we remember the square root. Okay. So, we calculate the square and we calculate the square root. So, if at some stage if v equal to 1, then that means what? V naught is the square root, right, and we have already ensured that v naught is not 1, because v was the first value for which the loop exited, right. So, v naught is not equal to 1. So, the other possibility could be that v naught is equal to minus 1. So, we check that whether v naught is equal to minus 1. If v naught is equal to minus 1, then that is also a failure, but if v naught is not equal to minus 1, then that means that v naught is neither plus 1 nor minus 1, but v naught square is equal to 1. So, that means v naught is a non-trivial square root of 1. Okay. And therefore, we do the previous thing, that is we take v0 plus 1 and compute the GCD with n, and that should give me one factor of n. This is how the algorithm works. Okay. So, now there are, first we shall, this is the algorithm. Okay. So, let us try to keep this algorithm in mind, and let us try to first of all analyze this algorithm. So, the first thing is that whether this algorithm at all terminates or not. Okay. So, how many steps do we maximum require to understand when it terminates? So, can you say me that whether we will at all get such kind of condition? That means, if so, you see that what we are doing is that we have got a while loop, like while v is not congruent to 1 modulo n, then this loop will continue. So, if v is never 1, then this loop will continue forever, right. So, can you tell me that whether if I take omega power r and continue such kind of powers, so what we are doing is that we compute omega r first of all, omega power r. Okay. So, what are the values in the series? We calculate w power r, then we calculate w power 2r, right, then we calculate w power 2 square r, and so on, right. So, at some stage we calculate w 2 to the power of tr, and so on, right. So, can you tell me that whether in this series there will be one value at least for which this value will be 1? So, that if that is so, then the loop will definitely terminate, right. So, therefore, can you reason it out that it will be definitely so? So, what is omega? Omega is an element, right. So, if omega is not necessarily primitive, it is a random choice, right. So, we have one result, if you remember, that omega power phi n, okay, is congruent to 1 mod n, right. And what is phi n? So, we had this ab minus 1 is equal to 2 to the power of s r, right. So, that means what? That is, so from here it follows, you see that is you have got omega power phi n is equal to 1 mod n, okay, and you have got ab minus 1 is equal to 2 to the power of s r, okay, and you know that ab minus 1 is equal to 0 mod phi n. So, what does it mean? That it means that phi n divides ab minus 1, which is equal to 2 to the power of s r, right. So, that means that phi n divides 2 to the power of s r, right. So, that means that if you find the w power of phi n is equal to 1, this means that w to the power of 2 to the power of s r should also be equal to 1 modulo n, right. So, that means that at least when this t value reaches s, right, then you should definitely get 1 1. Okay.
So, for this W should belong to the Zn star.
Yeah, W belongs, so you choose, this is a choice of W, the W is from 1 to n minus 1. It has been chosen so that 0 is not chosen and neither n is chosen. Okay. So, do you see why this loop will definitely terminate, right. So, therefore, there should be at least one value for which it will terminate. So, therefore, this algorithm is bound to terminate, it will definitely give you one result. Okay. But here you find that it can fail also, right. So, there are some values for which it can fail. So, there are two cases through which it can fail. One is that you find that W power r becomes equal to 1, right, and the other thing is that if for all these s exponentiations, so therefore, there are at most s exponentiations for this while loop. So, for all of these you find that it never returns minus 1 as a square root. Okay. So, if I analyze, but I am not going into the analysis, you will find that at most for n minus for n by 2 cases you will find that this can fail. Okay. So, that means the probability of success is at least half. Okay. And the proof is given in Stinson's book, you can see them, you can see that actually, see that it is okay, I mean it is a proof, so you can see that. So, therefore, finally that you will find that, so therefore, we have discussed about this, that it will terminate. The other important thing is about the correctness. Okay. So, therefore, whether this algorithm is correct or not. Okay. So, you see that the end of the while loop, what do you have? You have got two things. You have got, first thing is that V0 square, we have understood why it works, right, because you see that if V0 square is equal to 1 modulo n, that is at some point you get that, and you also ensure that if you do not get plus 1 and minus 1 for the values of the square, that is V0 is neither plus 1 or not minus 1, then by my previous what we have discussed about the factorization, we know that n can be factored by computing the GCD of V0 plus 1 and n. Okay. So, you can factor the values of n in this way. So, therefore, indeed V0 GCD of V0 plus 1 comma n will give you a factor of n.
So, how you are ensuring also that by that algorithm that V0 is not equal to 1 mod n?
V0 is not equal to 1 mod n. Okay. So, you see V is not congruent to 1 mod n is the condition. Okay. So, V0 is the previous value, right. So, therefore, if V is the least value for which this happens, then definitely V0 is not the, I mean I am not saying least means there is nothing least actually, because you are doing a modulo n, but what I am saying is the previous iteration value. So, the previous result cannot be 1 actually. Okay. So, that is the first, so therefore, V is the first value for which you have, I mean for which the while loop breaks. So, therefore, the previous value, that is V0, cannot be congruent to 1 mod n. Okay. So, this is quite okay. So, now we come to another interesting thing, is about the partial information of plain texts. Okay. So, therefore, sometimes the attacker can have modest goals. Okay. So, therefore, you may be interested in only to understand whether the input is even or odd, that is all. Okay. See, it can happen, right. So, therefore, and ideally a crypto system should prevent all sort of information leakage. Okay. So, therefore, we shall see that in case of RSA there are actually some informations which may leak, and there are some informations which should not leak. Okay. So, we shall see both the plus and minus actually. Okay. See, first thing is that you will find that the Jacobi of the plain text actually is leaked. Okay. And we shall also study about another two properties, that is the parity of the lowest bit of the plain text, that is whether the lowest bit is 0 or 1, and the other thing is that whether the plain text is less than or more than n by 2. So, therefore, what I am interested in is that whether it is more than half or less than half of n. Okay. So, we shall see that the first property is quite straightforward, the Jacobi of the plain text indeed leaks, whereas the second last two properties, that is the parity and the half problem, we call it the half problem, should not actually be easy to solve. Okay. If I assume that the RSA is a hard problem, that is the factor, I mean the factoring RSA is a hard problem. Okay. So, let us first of all understand this, why the Jacobi of the plain text is leaked. So, you see this, that is we know that the RSA function is like this, that is you take y and y is equal to x power b mod n. So, x is your plain text here and b is the encryption function, okay, encryption exponent. So, here everybody knows the value of b, right. So, you see that, so note that B is actually co-prime to phi n, right, that has to be shown. So, because we need the inverse of B, right, in mod phi n. So, therefore, in mod n. So, therefore, we see that phi n is actually equal to p minus 1 into q minus 1. So, what is p? P is, so p minus 1 is an odd term, I mean is an even term, and q minus 1 is also an even term. So, p minus 1 into q minus 1 is even, right. So, now if B is co-prime to this, then therefore B has to be odd, right. So, B is definitely odd, you see that. Is it okay? So, now what is the Jacobi of y by n? So, we know that from our definition, if n can be I mean if you know that y by n, you know that it is equal to x power b mod n, okay. So, we know that from definition y Jacobi n should be x Jacobi n power b, okay. So, therefore, now you know that this Jacobi, that is x Jacobi n, can be actually plus 1 or minus 1, okay. So, you remember that it can be either plus 1 or it can be minus 1, okay. So, this follows from the multiplicative property, you remember multiplicative property of Jacobi. So, from there it follows, and you know that the Jacobi of x, so therefore x Jacobi n can be either equal to plus 1 or minus 1. Why? Have you thought about this? What was the definition of Jacobi? N you can factor into p and q. So, what is the Jacobi of x given n, I mean x by n? If n equal to p q, then what is the Jacobi of x and n? It is equal to x p into x q, right. So, this value, how many, this is the Legendre symbol, right. So, how many possible values were there? 0, plus 1 and minus 1, right. So, 0 is excluded because in that case x was 0 mod p, okay. So, here also this is excluded. So, therefore, in this case it can be plus 1 or minus 1, okay. So, if it is 0 also, this is identically true because in that case the left hand side and the right hand side will also be 0. So, I am excluding the 0 case, the other two cases can be plus 1 or minus 1, okay. So, plus 1 and minus 1. So, therefore, now you see that if you have got x Jacobi n whole power b, then this value if you plug in plus 1, okay, then to the power of a odd number is also plus 1. If it is minus 1, you still get minus 1. Minus 1 to the power of odd is minus 1 yet, right. So, therefore, x by x and Jacobi n, I mean x Jacobi of x and n whole power b is equal to Jacobi of x and n. So, therefore, you see that the Jacobi of y and n is actually equal to the Jacobi of x and n, okay. So, that means that you see that without knowing also about a or b, or the main point is that b actually does not disturb this property, that is this encryption function does not change the Jacobi of x and n. So, therefore, the Jacobi of x and n is an invariant in RSA, right. You see that, right. So, therefore, the point is that RSA actually leaks some information on the plain text. If I say that RSA does not leak any information on the plain text, then it is not correct, okay.
How it is leaking information?
It is leaking because you know some value, right, you know that, okay, y without, you know some information of x and n. So, therefore, even say assume that if the encryption process did not take place, okay. So, then also you could have, you know the value of this Jacobi, right, Jacobi, but after the encryption also you know the exactly the same value, that is the Jacobi information is totally leaked, right. So, your cipher text and n has got the same Jacobi as that of your plain text and n, right, and that should not be the case, right. So, therefore, this is one possible leakage, but it does not mean that RSA is weak, okay. So, it just means that there is some information leakage, but whether, so information leakage is not the only thing, right, is not, I mean if you can actually exploit this information to get the secret, then that is an attack, right, but the thing is that there is a leakage of information, okay. So, now we shall discuss about, so we shall conclude our talk with these two properties, that is, one is called parity of y. So, definition is quite simple, it says that the low order bit of x, that is parity of y, is equal to 0 if x is even. So you see that I am interested in calculating the parity of y if x is even, and parity of y is equal to 1 if x is odd. So that means if I am able to find out the parity of y, okay, so you see that the input of this parity function is y, that is I do the encryption and after that I feed this to the parity function. If I am able to say whether it will be 0 or 1, which means that I am able to decide whether x was even or whether x was odd. So again that is another information of x, okay. And what about half of y? Half of y is equal to 0 if x lies between 0 and is lesser than n by 10, so therefore n by 2, so therefore x, so 0 is less than equal to x is less than n by 2, and half of y is equal to 1 if n by 2 is less than, this will be equal to, okay, n by 2 is less than equal to x is less than equal to n minus 1, okay. So both these intervals are closed actually, okay, but this is an open interval here. So the question is that whether you are able to solve these two problems, that is if you are able to solve, or if you have an efficient algorithm, a polynomial time algorithm for doing these two things, then definitely you are getting some information about the plain text, okay. So we shall see whether we can do that, and we will again apply some reduction techniques. Therefore what we shall show is that the existence of a polynomial time algorithm which will compute say the half y implies that existence of a polynomial time algorithm for the RSA decryption. So therefore if you are able to find out a polynomial time, a polytime algorithm which will compute half y, then you can actually find out a polytime algorithm which can do the RSA decryption, okay. So putting in the other way around, if RSA is hard, then this implies that computing the half y function is also hard, okay. So that is the counterpositive of this statement, right. So therefore you can do that. So the question is now whether how we can do that, and let us see, and without going into the algorithm, let us see why it is so, okay. So the idea is quite simple actually. So you see that, so how will I start? So what we have done till now is that we shall assume that there is an algorithm which is able to calculate this half y value, and we shall show that in that case we are able to find out the RSA, so we are able to find out the value of x, that is we are able to ascertain the value of the plain text, okay. So that means we are able to do the RSA decryption, okay. So we are not showing that we can factor n, so what we are showing is that we can actually calculate or determine the value of x, that is we can decrypt x actually in that case, I mean we can decrypt y, okay. So you see why. So can you tell me why? First of all, without going the algorithm, can you say me why? Like if I say half of y is say 0, so what does it mean? You can get a range. So you know that x lies between 0, closed interval 0 and n by 2 open interval, right. Then what you do? So you definitely you get that x, the entropy of x reduces, you see that, right. So now you have to do something like this. So what will you do? What comes to your mind? What you do is that you take x, okay, and you have to do some operation on x. Can you tell me, I mean some operation on y rather, can you tell me why? What?
You encrypt it with modulus n by 2 say RSA apply and then again call half.
Yeah, your idea is correct, but I mean this part needs to be solved, right. What you do is that you know the value of b, right. So what you do is that you multiply y with 2 power b, okay. So if you multiply y with 2 power b and apply the, so what is y? Okay, so what is y? Y is x power b mod n, okay, and if you multiply y with 2 power b, then what do you get? You get 2x power b mod n. So what is this? This is not just the RSA of, if I apply the RSA encryption on 2x, right. So now again if I ask the half oracle to find out the value of half, then that means that it will say me 0. If it says 0, then that means 2x should actually lie in the lower half, right. So that means x again gets partitioned into 2 parts, right, and then you can actually apply what? You can apply which search? You can apply normal binary search, right, to get the actual value of x, right. So this is the algorithm, right. So this is how the algorithm works. You see that if half of y is equal to 0, then x lies between 0 and closed interval 0 and open interval n by 2. Then what you do is that you take x power b and y, you know y equal to x power b, but you compute y equal to 2 to the power of b mod 2 to the power of b into y mod n, okay, and you know that this is equal to 2x whole power b mod n. So, now you ask the oracle half to find out the value of half y. Okay, so, half y equal to 0 implies that 2x will actually lie in 0 and n by 2. So, what does it mean? That x will either lie between 0 and n by 4, or it will lie between n by 2 and 3n by 4. Why 3n by n by 2 and 3n by 4? This is clear, right? 0 and n by 4, this is clear. Yes or no? First part is clear, right? If it is 0 n by 2, then straight away division gives you n by 4. This is also okay, I mean quite easy, because you say n by 2, you multiply with 2, you get n. You multiply 3n by 4 with 2, you get 3n by 2, but you are taking modulo n, right? So, therefore, it lies in the first half, right? Okay. So, you see that this is a clear partitioning. So, similarly, you can continue in this fashion and you will get 4 regions after this. Okay. So, depending upon the first choice, that is the first value gives you a 0 or 1. So, if suppose you get a 1 in the first iteration you get a 1, and in the second iteration you get a 0. So, that means which region should you search here? Second region, because 1 says that it is greater than n by 2, and second 0 says that it is in this region or this region. So, therefore, you search in this region, right. In this way you can actually narrow down your search and finally find out or determine the value of x, right. So, it is a very interesting algorithm, right, how you can do that, and it is also simple. So, therefore, continuing in this fashion we can actually obtain distinct boundaries of x, and therefore, you can actually obtain the value of x. So, putting in an algorithm form, it looks like this. So, you see that if there is a function which is the external half, and what you do is that you keep on iterating. So, therefore, you find out y equal to 2 to the power of b, and each time you ask the oracle half, okay, it gives you the value of hi, and depending upon the value of hi, whether it is 0 or 1, you do engage a simple binary search routine to find out the exact value of hi, the exact value of x. Okay. So, this is quite straightforward, and so therefore, the other question that we were asking is about the parity, right. So, actually the half and parity are actually polynomial equivalent, okay. That means both of them are same. Why? Because we have these two functions. So, I will not prove this, but these are two results, okay. So, therefore, you can say this like half of y, I can write like parity of y equal to ek2 mod n, and similarly parity of y you can also express in half function, okay, using the half function. So, so therefore, these two things gives you the reduction in both weights, right. So, therefore, you say that the parity of y is polynomially equivalent to computing the half y function, okay. So, can you say why this will work? Like if you know the value of parity y into ek2, then that is equal to half of y mod n. Why? I mean, what we have to do is that we have to find out when parity of y into ek2 mod n gives me a 0 and when it gives me a 1. Okay. So, you will find that y is what? Is x power b, and ek2 is also 2 to the power of b. So, this is what? 2x power b. So, this is ek. So, therefore, this parity will give me a 0 if 2x is even, right, and this will give me a 1 if 2x is odd, right. Similarly, the left hand side will give me a 0 when y lies in the first region, that is 0 to n by 2, and will give me a 1 when x lies between n by 2 to n, right. So, now you have to determine, just find out or rather argue that both are same, that is both the regions are same. Like if x lies between 0 to n by 2, then 2x is even, and if x lies in the higher region, then 2x is odd. So, actually this is quite funny, right, 2x is always even, but the thing is that when you are doing modulus n operations or congruences, then you get crazy results. If you do 2x, it is actually not even, right. So, mathematics can be quite funny actually in this type of things. So, actually I have detailed out the proof here for the first part, but the second part you can check. So, therefore, I am not going into this is simple, just solving the equations you can find out that whether why it is even and why it is odd. Okay. So, therefore, so you can easily find out whether these numbers are even in this region and the numbers are odd in the other region, and so this proves the first equation. Okay. So, I leave to you to actually solve the second equation. So, you can take that as a problem and you can try to solve that the second equality is also true. It is similarly you can prove it actually. Okay. Or should I show you this proof? Yeah, is it okay, right? So, therefore, I will conclude with this, that is, you can take this exercise that proves that the algorithm to factor n from the decryption exponent succeeds with at least half probability. You can just read this from Stinson's book, you should understand. And the other thing is that prove that the second relation to show that parity y and half y are actually polynomial equivalent. So, I have shown you the one part, the other part I have not. So, these are the references, okay, and I shall continue with discrete log problem.